There is something deeply wrong with the concrete under your feet. Right now, bridges are crumbling, highways are cracking, buildings less than 50 years old are being demolished because their concrete has failed. But in Rome, structures built 2,000 years ago still stand. The Pantheon, the Colosseum, aqueducts that carried water across empires. These weren't built with modern technology. No steel reinforcement, no chemical additives, just Roman concrete. And it's stronger today than the day it was poured. While your driveway needs repairs every decade, Roman harbors submerged in seawater for 2 millennia are growing stronger, not weaker, stronger. Scientists couldn't explain it. For centuries, they assumed Roman concrete was inferior, primitive, a lucky accident. Then in 2023, researchers at MIT and Harvard finally cracked the code. What they found wasn't luck. It was engineering genius that makes modern concrete look like a failed experiment. And the construction industry has known about this for decades, but continues building with inferior materials because Roman concrete has one fatal flaw. It's too good, it lasts too long, and that's terrible for business. Before we go deeper, drop a comment and tell us, have you seen concrete failing around you? Cracked driveways, crumbling buildings, potholed roads? Let us know below, because what you're about to discover will change how you see every modern structure. Let's start with the concrete you think you know. Modern concrete is a mixture of cement, sand, gravel, and water. The cement, usually Portland cement, is made by heating limestone and clay to 1450 degrees Celsius. This process creates a powder that, when mixed with water, forms a paste that binds the aggregate together. It's fast, it's cheap, and it's everywhere. Your home's foundation, the roads you drive on, the bridges you cross. Over 10 billion tons of concrete are produced every year. It's the most used substance on Earth after water. But here's the problem. It's failing catastrophically. In 2021, a condominium in Miami collapsed, killing 98 people. The concrete had degraded after just 40 years. In 2018, the Morandi Bridge in Genoa, Italy, collapsed during a rainstorm. 43 people died. The bridge was only 51 years old. Across the United States, over 42,000 bridges are structurally deficient. Most were built in the 1960s and 70s. They're barely 50 years old, and they're already dangerous. Modern concrete has a design life of 50 to 100 years. But in reality, most structures start showing serious degradation after 20 to 30 years. Cracks appear, water seeps in, the steel reinforcement inside rusts and expands, causing more cracks. It's a death spiral. The primary culprit is a chemical reaction called carbonation. Carbon dioxide from the air reacts with calcium hydroxide in the concrete, forming calcium carbonate. This lowers the pH, which corrodes the steel reinforcement. Add salt from roads or seawater, and the process accelerates. Then there's freeze-thaw damage. Water gets into cracks, freezes, expands, and makes the cracks worse. Each winter, the damage compounds. Modern concrete also suffers from alkali-silica reaction. Certain aggregates react with alkali in the cement, causing expansion and cracking from the inside. Engineers know all of this. They've tried everything. Adding polymers, using fiber reinforcement, coating with sealants. Nothing stops the decay. It only slows it. So we accept it. We budget for repairs. We plan for replacement. We've normalized the idea that concrete is temporary. But Romans didn't think that way. They built for eternity, and they succeeded. Roman concrete, called opus caementitium, was fundamentally different from what we use today. The recipe was simple but precise: volcanic ash, lime, seawater, and rock aggregate. The volcanic ash came from Pozzuoli, near Naples, a region rich in volcanic deposits. Romans called it pulvis putiolanus, or pozzolana. This ash was the secret. When mixed with lime and water, pozzolana underwent a chemical reaction that created an incredibly durable binder. Unlike modern cement, which sets through hydration, Roman concrete set through a slow, pozzolanic reaction that continued for years, even decades after pouring. This meant the concrete didn't just harden. It evolved. It improved with age. The lime was made by heating limestone to around 900 degrees Celsius, much lower than the 1450 degrees needed for modern Portland cement. This made production less energy-intensive. Romans mixed the pozzolana and lime in roughly equal proportions, added seawater in coastal areas, and combined it all with chunks of volcanic rock called tuff. The mixture was thick, more like a dense mortar than modern concrete. They poured it into wooden forms and left it to cure. No vibration to remove air bubbles. No admixtures to speed setting. Just time and chemistry. The result was a material that gained strength over centuries. The Pantheon's dome, built in 126 AD, is still the largest unreinforced concrete dome in the world. It has survived earthquakes, floods, and nearly 2,000 years of weathering without significant cracks. Modern concrete domes require steel reinforcement and still don't last a fraction as long. Roman harbors are even more impressive. The harbor at Caesarea, built by King Herod around 15 BC, used concrete piers submerged in seawater. Seawater is one of the most corrosive environments for modern concrete. Salt accelerates steel corrosion and chemical breakdown. Engineers today go to extreme lengths to protect marine concrete, using special cements, coatings, and cathodic protection systems. Yet Roman concrete not only survived in seawater, it thrived. In 2017, researchers from the University of Utah analyzed samples from Roman marine structures. What they found was shocking. The concrete wasn't just intact, it had grown stronger. Seawater had triggered a rare chemical reaction. The pozzolana reacted with seawater to form aluminum tobermorite, an extremely rare and exceptionally strong mineral. This mineral grew within the concrete matrix, filling microscopic cracks and voids, reinforcing the structure from within. It was self-healing concrete. Modern science couldn't replicate this for 2,000 years. Let's talk about what makes Roman concrete indestructible. The key is the pozzolanic reaction. Modern Portland cement relies on calcium silicate hydrates for strength. These form quickly when cement and water mix, giving concrete its initial hardness. But this reaction also creates calcium hydroxide as a byproduct. Calcium hydroxide is soluble and vulnerable to carbonation and acid attack. It's the weak link. Roman concrete used a different chemistry. The volcanic ash contained high levels of silica and alumina. When mixed with lime and water, these compounds reacted slowly to form stable calcium aluminum silicates. No calcium hydroxide byproduct. No weak link. The reaction was slow, sometimes taking years to complete, but the final product was chemically stable and resistant to attack. Then there's the role of seawater. Modern engineers avoid seawater in concrete because the chlorides corrode steel reinforcement. But Romans didn't use steel. They didn't need it. The seawater, rich in minerals, reacted with the pozzolana to create tobermorite and philipsite crystals. These minerals are incredibly dense and strong. They filled gaps in the concrete matrix, creating a material that was less porous and more resistant to chemical attack. Researchers at the Lawrence Berkeley National Laboratory used advanced imaging techniques to study Roman concrete at the nanoscale. They found that the mineral structure was interlocking and self-reinforcing. Cracks that formed due to stress or weathering would trigger further pozzolanic reactions, essentially allowing the concrete to heal itself. Modern concrete does the opposite. Once a crack forms, it's a pathway for water, oxygen, and chemicals to penetrate deeper. The damage compounds. There's no self-healing mechanism. Engineers have tried to create self-healing concrete by embedding bacteria or capsules of healing agents, but these are expensive, unreliable, and add complexity. Roman concrete healed itself naturally, using nothing but the materials at hand and the chemistry of seawater. The temperature of curing also mattered. Modern concrete cures best at controlled temperatures around 20 to 25 degrees Celsius. Extreme heat or cold can weaken it. Roman concrete was more forgiving. The slow pozzolanic reaction meant it could cure in a wider range of conditions. Romans built in scorching Mediterranean summers and cold alpine winters. The concrete adapted. So why don't we use Roman concrete today? The answer is depressingly simple: speed and money. Modern construction is driven by deadlines and budgets. Portland cement sets in hours. You can pour a foundation in the morning and start building on it the next day. Roman concrete took weeks, sometimes months, to reach full strength. No modern developer wants to wait that long. Labor costs would skyrocket. Projects would be delayed. Profit margins would shrink. So we use fast-setting cement, knowing it won't last. We build structures with planned obsolescence. Bridges need replacement every 50 years. Buildings are demolished and rebuilt. It's not a bug. It's a feature. The construction industry thrives on this cycle. If we built with Roman concrete, if we constructed bridges and buildings that lasted 2,000 years, there'd be no repeat business, no constant repairs, no lucrative reconstruction contracts. Then there's the issue of raw materials. Pozzolana isn't available everywhere. You need volcanic ash with specific chemical properties. Romans had easy access to the deposits near Naples. Modern builders don't. Transporting volcanic ash globally would be expensive. So instead, we use Portland cement, made from limestone and clay, which are abundant everywhere. It's a compromise. Performance for convenience, durability for cost. Engineers know Roman concrete is superior. Studies have proven it. Universities have recreated it in labs. It works. But changing an entire industry is nearly impossible. Concrete standards, building codes, contractor training, supply chains, everything is built around Portland cement. Switching would require a complete overhaul. And the political will isn't there. Because the people making decisions aren't thinking about 2,000-year lifespans. They're thinking about quarterly profits and election cycles. There's also an environmental factor. Portland cement production accounts for 8% of global CO2 emissions. It's one of the most polluting industries on Earth. The high-temperature kilns needed to make clinker burn massive amounts of fossil fuels. Roman concrete, made with lime fired at lower temperatures, produced far less CO2. If we switch to Roman methods, we could cut emissions from concrete production by half or more. But the industry resists. Change is slow. Inertia is powerful. And the profits from the current system are too large to abandon. You can't rebuild your house with Roman concrete, but you can learn from the principles. First, if you're building or renovating, seek out alternatives to standard Portland cement. Pozzolan-based cements are available. They're marketed as blended cements or supplementary cementitious materials. They cost slightly more, but last significantly longer. Fly ash, a byproduct of coal power plants, has pozzolanic properties similar to Roman volcanic ash. Concrete made with fly ash is stronger and more durable. Slag cement, made from blast furnace waste, is another option. These materials mimic the slow, strong curing of Roman concrete. Second, avoid using concrete in aggressive environments without proper protection. If you're near the ocean or in areas with heavy freeze-thaw cycles, invest in high-quality sealants and coatings. Or better yet, use materials that don't degrade. Stone, brick, timber treated properly. Romans used concrete where it made sense and stone where it didn't. Third, support research into sustainable, durable concrete. Universities and startups are working on bio-based cements, geopolymer concrete, and other alternatives. These technologies need funding and public demand to scale. Finally, demand better standards. Write to your representatives. Ask why bridges are failing after 50 years when Roman structures last 2,000. Demand infrastructure built to last, not built to be replaced. Every time a bridge collapses, every time a building is demolished because the concrete failed, it's a failure of priorities. We chose speed over longevity, profit over performance, and we're paying the price in lives, money, and environmental destruction. If you're learning something valuable here, hit that like button and subscribe. The Romans didn't discover a magic formula. They used the materials they had and understood the chemistry deeply enough to create something that worked with nature, not against it. Modern concrete fights chemistry. It tries to force durability through additives and coatings, but it's fundamentally flawed. Roman concrete embraced chemistry. It used slow reactions, natural minerals, and environmental conditions to build structures that improved with age. The Pantheon has stood for 1,900 years. Your driveway cracks in 10. That's not progress. That's a betrayal of engineering principles. The knowledge wasn't lost. It's in every Roman ruin, every ancient harbor, every structure still standing after 2 millennia. We just chose to ignore it. Because buildings that last forever don't generate revenue. Bridges that never need replacement don't create jobs. Concrete that heals itself doesn't need an industry to fix it. But that's exactly why we need to bring it back. Subscribe. And let's keep uncovering what modern industry buried. Because the Romans proved something we've forgotten. Buildings don't have to crumble. Infrastructure doesn't have to fail. Concrete can last 2,000 years. We just have to be willing to build for the future, not for the next quarterly report.